Hi, welcome to the video on absorption and emission spectra. So the success criteria for this video is to describe how absorption and emission spectra are generated. You're going to learn how to read the electromagnetic spectrum, especially the visible region. You're going to use emission or absorption spectrum to identify an unknown. And here are some key terms that will appear throughout the video. So let's start with an analogy to help us understand absorption spectra. If you were performing a box jump, would you require energy to do this box jump, or would you release energy while doing it? Right. Doing a box jump requires energy, because your body needs energy to jump to an elevated surface. Likewise, electrons need energy to jump from a lower energy level to a higher energy level. Now, whereas humans must consume food to provide energy to do a box jump, electrons must absorb energy from light, also known as electromagnetic radiation, or electric current, or heat to jump or transition to a higher energy level. However, electrons can only absorb certain amounts of energy because electron can only exist at discrete or quantized energy levels, not in between. So as we can see here on the right, that the electrons are located on the energy levels, and you wouldn't find them in between. That's similar to when you're walking up the stairs. Your feet can only rest on a step, not in between steps. So the stairs are quantized. A ramp, on the other hand, is not quantized because your feet can rest anywhere along the ramp. Now, the size of the gap between energy levels determines how much energy the electron needs to absorb. A larger gap would require more energy, and a smaller gap requires less energy. Take a look at these two electrons that are undergoing transitions. Which electron, A or B, would need to absorb the least amount of energy to make the transition? That's right, electron B, because the gap between the energy level, where it's starting and where it's going to, is smaller than in electron A. So how do scientists know that the energy of electrons are quantized? The evidence comes from studying the interaction between light and atoms. So let's pause to talk about light, also known as electromagnetic radiation. Take a moment to write down what you already know about light. Well, some things you likely know about light is that white light is made of different colors. So if you shine a white light through a prism, then it will split apart into different colors and appear as a rainbow. You may also know that light is bright, it can feel hot, and natural sources of light are sun and stars. But what exactly is light? We said it's called electromagnetic radiation. And the reason why it's called electromagnetic radiation is because light contains oscillating electric and magnetic fields. Light also has a dual nature. It behaves like a particle and a wave. The particle component of light is known as a photon. Now, all things in actuality have a dual nature, including you. You have a particle component, which is probably your nature, which you are most associated with yourself. And then you also have a wave component. However, because you're so large, your wave component is insignificant. But things like photons and electrons, which are super small and on the quantum scale, their wave component is significant. And just a reminder that a wave transports energy. Now, there are different types of light, as shown by the electromagnetic spectrum. So you have gamma rays, X-rays, ultraviolet or UV light. You have visible light, infrared, and radio waves. Now each type of light can be described by these three properties. Its energy, frequency, and or wavelength. Now those three properties are related to each other by a couple of light equations. So let's see the relationship between energy and frequency. According to this first equation, energy is equal to Planck's constant, given the symbol h, times frequency, given the symbol nu. So energy is equal to Planck's constant times frequency. It's clear that energy and frequency are directionally proportional because if you increase the frequency, then the energy will increase by that same factor. Now let's look at energy and wavelength. Well, they're inversely proportional, and let's see why. So here's the equation. Energy is equal to Planck's constant times the speed of light divided by the wavelength, which is given the symbol lambda. If you increase the wavelength, because it's in the denominator, the energy will decrease by the same factor. So that would mean if you double the wavelength, for example, the energy will decrease by half. So when we're looking at this electromagnetic spectrum, and as we go across, we notice that the wavelength is increasing because the distance between the waves are getting longer. But we can also tell that because the energy and frequency are decreasing. And so if energy and frequency decrease, the wavelength must increase, since they are inversely proportional. So the part of the electromagnetic spectrum which we're probably most familiar with is visible light. Red light, as you can see, has the longest wavelength. Its range is from 625 to 740 nanometers. So let's take a moment to talk about what a nanometer is. So when we say wavelength, we're talking about the distance either between two crests of a wave or two subsequent troughs. And a nanometer is equivalent to 1 times 10 to the negative 9 meters, or 0.000, like basically 8 zeros to the right of the decimal, 1 meters. Now, if we're talking about 500 nanometers, and if you notice that the visible region is in the order of hundreds of nanometers, then that will be times 10 to the minus 7. So as I said, red light has the longest wavelength of all the visible light, and thus it has the lowest energy. On the other hand, violet light has the shortest wavelength, and thus has the highest energy. So how does light relate to electrons? Because electrons can absorb discrete energy of light to jump to a higher energy level, we can use the energy of the light the electron absorbed to determine the gap between each level. So let's take a look at that. So we have an electron that jumped from the first to the 5th energy level. 1, 2, 3, 4, 5. Now in doing that jump, if the electron absorbs violet light at a wavelength of 400 nanometers, which if we use those light equations, would correspond to an energy of 5 times 10 to the negative 19 joules, or 3 electron volts, then the difference in energy, or the gap between the 1st and 5th energy level, would be 3 electron volts. So we can again measure this energy gap by knowing the light that the electron had to absorb to make that transition. In fact, that's how Niels Bohr came up with the Bohr model. He studied the energy of light associated with electron transitions and determined the energy between energy levels. So in his experiment, Niels Bohr used a spectrophotometer, a device that measures the light absorbed or emitted by a sample. A spectrophotometer can produce 2 types of spectra, an absorption spectrum or an emission spectrum. Spectrum, or plural spectra, is an image that shows the wavelength of light emitted or absorbed by matter. So we're going to take a look at the different types of spectrum, but let's take a moment to see if we can figure out which spectrum shows an absorption, a continuous spectrum, or an emission spectrum. Let's look at a continuous continuous spectrum. You've actually seen this before. So once again, if you take something like white light and you shine it through a prism, the light breaks apart and it appears like a rainbow. This rainbow is a continuous spectrum because it has all wavelengths of light with no breaks or gaps in between. Now let's look at emission absorption spectrum, starting with absorption. So if you have an atom and it has electrons in the atom, and you shine light such that the electrons absorb that light, the electrons can jump to a transition that again corresponds to the energy of light they absorbed. So let's say violet light will move the electron up to the 5th level. Because the electron absorbed that light, it's no longer in that continuous spectrum. It got absorbed, so it appears as a black line. If this electron absorbs blue light to transition up to the 4th energy level, then again, that disappears. Same thing with the green light, and same thing with the red light. So what happens in an absorption spectrum, you'll have black bands appearing in what looks like a continuous spectrum. And it's called an absorption spectrum because it shows the frequency of light absorbed by the atoms. So key things to know about absorption spectrum. Absorption spectra are generated when electrons in atoms absorb light and transition to a higher energy level. Only the light whose energy corresponds to the energy of the electron will be absorbed. The light that gets absorbed shows up as black bands in the absorption spectrum. Now what about emission spectrum? Well, in emission spectrum, you're actually starting with electrons at excited state, so they're at a higher energy level. They're already absorbed energy, but they don't want to stay there, so they're going to transition back down. And when they transition back down, when they drop back down, they release energy, and that energy will appear once again as the light that corresponds to that energy gap. So going, let's say, from the 4th to the 1st, maybe it emits blue light. Going from the 3rd to the 1st, maybe it emits green light, and so on. So an emission spectrum is generated when the electron drops down to a lower energy level and releases light that corresponds to that energy gap. And it's called an emission spectrum because it shows the frequencies of light emitted by that atom. Key things to know about emission spectrum. To get an emission spectrum, electron must first absorb energy in order to transition to a higher energy state, because remember, they're dropping down. However, the emission spectrum is only generated when the electron drops back down, not when it goes up, but when it drops back down, thus emitting or releasing energy in the form of light. So the steps for generating emission spectrum: first, you need to excite the electron. And you can excite the electron by having it absorb energy as light, electric current, or heat. 2, the excited electron, being unstable, has to drop down to a lower energy level. It doesn't necessarily have to be its original energy level, it just has to be a lower energy level. And 3, you record the wavelength of light emitted or released by the electron when it drops down to a lower energy level. And that's how we generate an emission spectrum. So now let's take a look at this again. Which spectrum shows absorption, continuous spectrum, or emission spectrum? I'm sure you got it now. Now let's take a closer look at the absorption and emission spectrum for the same atom or element. What do you notice? You probably notice that the bands match up. The black bands in the emission spectrum and the color bands in the absorption spectrum, the black bands in the absorption spectrum and the color bands in the emission spectrum match up. And that makes sense because it doesn't matter the direction of the transition, whether the electron is jumping up or dropping down. The energy gap will remain the same, and thus the energy of light that's absorbed or emitted will remain the same. Now the cool thing about emission absorption spectra are that they are like fingerprints.